Okay, thank you very much. So I would like to thank the organizers for inviting me here. So what I'm going to talk about today is supersymmetric index of small black holes, and this is work done in collaboration with Chandramouli Choudhury, Shanmugapriya and Amita Virmani, and there is also related work by Chen Murthy and Turiachi, and I'll try to make in some more detail the connection between our work and their work at the end of the talk. So let me begin by reviewing a few properties of black holes that we are all familiar with. So we'll consider, to begin with, a black hole in a two-derivative theory in d dimensions. And such black holes can carry a set of U1 charges depending on how many U1 gauge fields you have in the theory, which I'll denote by Q. It can carry angular momentum in the Cartan subalgebra of SO d-1, and of course it has some mass. And the Bekenstein-Hawking formula for the entropy is given by this form, the area of the event horizon over 4 times the Newton's constant. And this can be expressed as a function of the charge that the black hole carries, the mass and the angular momentum. And here I have not added the moduli, which are the vacuum expressions of the various scalar fields at infinity, which we will take to be fixed. And in general, Q and J can have multiple components, because you can have multiple U1 gauge fields, and J for sufficiently large D, the Cartan generator, there may be more than one Cartan generator of SO d-1, so that it gives multiple components of J. Now, for two derivative theories, there is a special property, which is the scaling property of the action. So if we scale the various fields, okay, which is the metric, the two-form field, the gauge field and the scalar fields in this way, then the action scales as lambda to the d-2. And from this we can also derive a simple scaling property of the entropy in d dimensions. And that says that if we scale up the charges, the mass and the angular momentum by these powers of lambda, then the entropy scales by an overall factor of lambda to the d-2. And this makes it easy to take the macroscopic limit. So while macroscopic limit means you want the black hole to be large, and that can be achieved by simply scaling the masses, charge and angular momentum in this way, and then take lambda to be large. And in this limit the black hole becomes big and the entropy scales as lambda to the d-2. And typically our goal has been to compare the entropy with the log of the degeneracy. And this side, log of degeneracy, has to be counted from some microscopic counting of the degeneracy of states. We also introduce chemical potentials, okay, the generalized chemical potentials, which includes the inverse temperature beta, defined this way, the chemical potential dual to the charges, which are defined this way, and the chemical potential dual to angular momentum, which is also known as the angular velocity, which is defined this way. And because angular momentum has multiple components, typically the angular velocity also has multiple components. And from the scaling properties that we saw earlier, okay, the fact that the black hole entropy scales as lambda to the d-2 under these scalings of mass, charge and angular momentum, one can figure out the scaling properties of beta, mu and omega. And these are important because in gravitational path integral, we take beta, mu and omega to set the asymptotic boundary condition of the path integral, and these are taken to be independent variables. Yes.
Is the power of the non-press the same for J from the previous term?
Oh no, J should be lambda to d-2. Yeah, there is a typo. Yeah, J goes as lambda to d-2. Thank you. And another important fact that you should note for now is that once we go beyond two derivative action, okay, by adding higher derivative terms, then the black hole entropy formula is modified, and there is a generalized formula known as the World's formula. So this gives correction to the entropy from the classical higher derivative terms, and as a result the scaling properties are modified. So the World's entropy doesn't scale in the same way as the Bekenstein-Hawking entropy, because it includes the effect of higher derivative terms in the action. Now, this equality between entropy and log of degeneracy has been tested in many examples in string theory. However, there remained one open issue, Okay, and so this started with this work of Strominger and Vafa that you have already heard of in the morning. Okay. And the issue that remained is that the computation of degeneracy is done by representing the black hole states as states of some brane system, and that carries the same charge as a black hole. That's how you fix the brane system that you want to study. But the dynamics of the branes is understood at weak coupling, and that's where the counting can be done. On the other hand, the black hole description is valid only when the gravitational coupling is strong enough so that the horizon size exceeds the Compton radius, okay, so that the quantum fluctuations remain confined within the horizon. Okay. And so these two seem to be contradictory, because in one case we need the coupling to be arbitrarily small, in the other case we need the coupling to be large enough so that the horizon radius is big enough. Okay. And the question arises that if this is the case, then how can I compare the two expressions? Okay. And this was answered from the early days. And that is, the strategy is to try to compare supersymmetric index of BPS systems. And the reason that you want to compare supersymmetric index of BPS systems is because, unlike the degeneracy, the supersymmetric index is protected and does not change as we vary the coupling constant. So in principle, we can calculate the supersymmetric index at weak coupling by representing this as a brane system, and presumably we may be able to calculate supersymmetric index as strong coupling from the black hole side. Okay, and this I'll elaborate on this more in the next slide. So on the microscopic side, when you represent the system as a brane system, we can easily compute the index because we are just counting states, right? So we can always weight by -1 to the f, right? That's what the index does. But on the black hole side, we usually calculate the degeneracy, okay, because you don't calculate the index directly. The entropy, black hole entropy, is a log of the degeneracy and not a log of the index. And one of the assumptions that one makes in making this comparison between the microscopic index and the black hole entropy is that the index and degeneracy are equal at generic coupling. Okay, and we believe that the black hole entropy can be calculated at a generic coupling. Okay. And then we can just compare the log of index calculated from the microscopic side with log of degeneracy calculated from the black hole side. One can give some additional justification for this, okay, why the black hole index and degeneracy are the same. Okay. But these additional justifications, okay, are given based on the near horizon ADS2 geometry and supersymmetry. Okay. But typically this is subject to corrections by modes that live outside the horizon. Okay, so while one can argue that as far as the modes associated with the horizon are concerned, okay, the index and degeneracy should be the same for the black holes. Okay, but the black hole can also have modes living outside the horizon, and their contribution to the index is not necessarily equal to their contribution to the degeneracy. Okay. So one would like to do better, okay, and the question is it possible to do better by computing the index directly on the black hole side? And this is what Samir explained in the morning. Okay, so what I'm going to do in the next slide is to just give the algorithm, okay, for computing the index from the black hole side without giving the derivation. So here is what one calculates. Okay, this is a prescription. Okay, so for this talk, you just take this as a prescription for computing the index from black holes. So you construct an Euclidean black hole for which an appropriate component of the chemical potential or of the angular velocity satisfies this relation that omega is -2 pi I over beta. Now what do you mean by appropriate component? Okay, so what we do is that we take the angular momentum to lie in a two-dimensional plane, in any two-dimensional plane, doesn't matter, okay, but you fix a two-dimensional plane, let the angular momentum take value in that two-dimensional plane, and then the chemical potential is defined corresponding to that two-dimensional plane. Okay, other angular momentum is set to 0, other components. Then the claim is that the SBPS, which I'll define as the log of the index, okay, computed from the black hole side, is given by this formula over here. Okay. So it's a sum of the world entropy. Okay, here I am not assuming that you are in two derivative theory. Okay, include all classical corrections, alpha prime corrections. So it's a sum of the world entropy plus 2 pi ij plus quantum corrections. Yes.
What would you do in a 2D theory of gravity where you don't have a plane rotation?
Yeah, in 2D theory it's hard because you cannot associate -1 to the f to j. Right? So this will be in higher D. So D larger than or equal to 4. Okay, so this is a formula. Okay. As we will see, for the purpose of this talk, we will not need to worry about quantum corrections. Okay. So the relevant part of the formula that we will have to use is this. Okay. And this is what we will try to use to calculate the index on the black hole side. Okay. So the strategy is that we can calculate the log of the index by this formula and compare it with the microscopic results. Now one point I should emphasize here is that when once you impose this condition omega equal to -2 pi I over beta, this gives you one condition between these parameters. So that essentially fixes m in terms of q and j. But j still remains an independent parameter on the right hand side, right? This depends on j, this depends on j. M is fixed. But on the left hand side, it depends only on the charge. So it's a non-trivial constraint. Okay, or non-trivial check that once you calculate the right hand side, it becomes independent of j. Okay, so now we are going to apply this to a specific problem. Okay, and the specific problem that we'll be dealing with is to represent the fundamental string states as black holes. Okay, so let me explain this notion of how to get BPS states from elementary strings. Okay, again, this is something that Samir explained in the morning, but I'll do this again for this talk. So we'll be considering heterotic string theory compactified on a 10 minus d-dimensional torus. Okay, but this can also be generalized easily, okay, to compactifications on k3 times t2, okay, or k3 times s1, and I'll discuss this at the end. Okay, the results don't change. Okay, it's identical analysis, but just for definiteness, we'll focus on this problem. Heterotic string theory compactified on 10 minus d-dimensional torus. So this will describe a theory in d non-compact spacetime dimensions. Now the spectrum of the elementary string contains states that are charged under various U1 gauge fields in the theory. These U1 gauge fields come from the original E8 times E8 or S32 heterotic string, and they can come also from the components of the metric and the two-form field along the compact circles. So we denote by Q the charge vector, okay, the set of all the charges, and a subset of these states turn out to be invariant under half of the supersymmetries of the theory, and these are called the BPS states. As we go high in charge, they have large degeneracy and index, and the question is, can they be described as black holes carrying the same charge vector Q? And one of the tests will be that the log of the index should agree with the log of the index that we calculate from the black hole side. So now I am going to give the microscopic formula for SBPS. SBPS, if you recall, is defined as the log of the index. So the microscopic formula for SBPS is given here. Okay, it's completely explicit. Here Q square is a specific quadratic function of the charges. In the language that Samir used in the morning, Q square is 2n times W. Okay, it's the product of the momentum and winding along the circle times 2.
If you want the log to be I, e to the 2 pi log tau.
E to the
right equation.
here?
No, the equation is.
Here?
No, the right, go to the right.
I and tau. Yeah. Yeah, so this is the definition of the Dirac eta function. So the point is we have the explicit expression for the Dirac eta function, and this index is essentially the Fourier coefficients of the Dirac eta function. Right? This is just taking the Fourier transform of the minus 24th power of the eta of tau. Okay, so it's very explicit. Okay. If you want to calculate the result for any particular q square, you can just expand it out and read out the coefficients. Okay. But more importantly, we can also figure out the large q square behavior of this of e to the SBPS, and SBPS turns out to be 2 root 2 pi square root of q square plus corrections which are suppressed by powers of q. Okay. And again, to make connection with Samir's result, okay, q square, if you set q square equal to 2 nw, you see that we get 4 pi square root of nw. Okay. That's exactly the result that Samir mentioned in the morning. Okay. So one difference is that we will be considering the theory in arbitrary dimensions, okay, whereas he analyzed the theory in 4 dimensions. So here is the result again, okay, and the question that we'll be interested in is, can we compare this with BPS black hole entropy carrying the same charge? So the entropy comparison to the BPS black hole entropy has a long history, okay, spanning 10 years, okay, but this will not be reviewed today. Okay. Instead, we are going to change the question. Okay. The question that we will be asking is it possible to compare SBPS to the log of the corresponding formula for SBPS that the black hole gives. Okay. As we discussed, the log of the index computed from the black hole side is given by the world entropy or the black hole entropy. Okay, let's start first with the Bekenstein-Hawking entropy plus 2 pi ij, okay, at omega equal to minus 2 pi by I by beta. Okay, so this is the first attempt we will make, okay, to compare this with the entropy that you calculate from the or the log of the index that you calculate from the black hole side. Now, before we start doing the actual calculation, let's just study the scaling properties. Right? So we have this scaling property here, okay, which we give. Now, microscopic result says that SBPS should be given by this. And from the scaling property that is here, you can see that SBPS scales as lambda to the d minus 3.
I'm very sorry, but
yeah.
in the second transparency, the power of lambda for j was d minus 3. I think
Yeah, that was wrong. Yeah, so the first one was correct.
Okay, so then I'm confused because when lambda is round, could j exceed m?
Yeah, I think this is in d dimensions, right? In, let's see.
J equals m squared.
Oh,
Yeah,
oh,
yeah,
okay, I see.
yeah.
I see.
So I think this is fine, yeah. Okay, so if you now compare, okay, on the microscopic side, we see that the SBPS goes as lambda to the d minus 3, right, because it's square root of q square. On the other hand, on the macroscopic side, okay, we have the Bekenstein-Hawking entropy scales as lambda to the d minus 2, J scales as lambda to the d minus 2. So naively we would expect that this sum will be of order lambda to the d minus 2, and it's certainly much larger than SBPS. Okay, so that seems to be a contradiction. So to see what's going on, let's just calculate and see what we get. Right? We can calculate the black hole solution explicitly, construct the black hole solution explicitly, calculate SBH and 2 pi ij and see what we get. Okay, so here is the action and the solution. Okay, the action is the action for n equal to 4 supergravity in d dimensions. Okay. It's not perhaps important what these various things are. So basically, the fields have a metric. Okay. Then the dilaton phi. Okay, there is a matrix valued scalar field which captures the internal moduli of the torus. Okay. Then you have the free form field that comes from the curl of the two form. But the important point is that the solution is known. Okay, this is the solution. I have already written it in the Euclidean framework, and I have also set the omega beta equal to minus 2 pi I already. Okay, so this solution already has been evaluated there. Okay. Horizon is at rho equal to b. Okay. The important part is here. Okay. So for this solution, one can calculate the charges. And square root of q square is given by this combination here. CD is just an overall normalization factor of the action, which you can identify as 1 over 16 pi gn. So square root of q square is given by this formula over here, okay, where omega k is the volume of the unit k sphere, you see omega d minus 2. The black hole entropy is given here, okay, and J is given here. Okay. This parameter B is the extra parameter that is there in J. This is the parameter that parameter is the angular momentum. I said that the right hand side, okay, explicitly is BH as well as J depends on an extra parameter, that is this parameter B. Okay. But now when you calculate SBH and SBH plus 2 pi ij, okay, you see that these two terms exactly cancel and you get 0. Okay. So this then avoids inconsistency, right? Because we had said that these scales at a lower rate than SBH and J together, right? So if this hadn't cancelled, then it would be a definite contradiction, because this side will go as lambda to the d minus 2, whereas this goes as lambda to the d minus 3.
The solution is just Kerr-Newman in D dimension with appropriate charge.
Solution is Kerr-Newman in D dimension. Okay, it's not Kerr-Newman because they are also scalars, right? So it's a generalization of the Kerr-Newman, but it can't be explicitly constructed in the theory. Okay, so to proceed further, we need to recall that string theory, of course, has higher derivative correction to the low energy effective action, right? So we are still not done because there is a contradiction, right? On the right hand side, the microscopic result goes as lambda to the d minus 3. Okay, this one is 0. Okay, so you have to get some non-zero answer on this side. So let's look at the next order term. What is the effect of the higher derivative correction? So the next order term contains 2 extra derivatives, okay, because you go from 2 derivative to 4 derivative. Okay. And so these 2 extra derivatives will contract with the G with upper index mu nu. Okay. And because the metric scales as lambda square, we see that G with 2 upper index will go as 1 over lambda square. So the next order correction to the world entropy will be suppressed by additional power of 1 over lambda square. So since at leading order, these go as lambda to the d minus 2, okay, the corrections will go as lambda to the d minus 4. Okay. So after taking into account the correction due to 2 derivative terms, we expect that this combination will scale as lambda to the d minus 4, which now is much less than the expected result for BPS entropy. Yes. Yes. So SBH is non-zero.
But J is the angular momentum.
J is the angular momentum. But it's imaginary. This is we are working in the Euclidean space with imaginary parameter.
But it's the rotational parameter of the black hole, right? So I have mass, charge, angular momentum.
Yes. But SBH plus 2 pi ij is 0. I mean, you are thinking of that as a why is it a contradiction?
Because I have Q.
You are looking at a fixed charge, right? We calculate the black hole entropy and the yes. So this is non-trivial that it is true, right? But you have to calculate SBH and 2 pi ij separately, and you find that the sum is 0.
What I'm confused is that if I set the angular momentum equal to 0,
Yes.
this is how it rises up from black hole, for which SBH is not.
But you have to set the chemical potential to be 2 pi I over beta, right? Omega, the small omega, which is the angular velocity, has to be, yeah, so you cannot just set this to be 0. Yeah. Yeah. So it's only for that this combination vanishes. Yeah. Thank you. Yes.
If I had taken omega to be 6 pi I over beta, would I also get this?
No.
So
it's 2 pi I over beta is very special, because some of the point is if we take omega to be anything other than 2 pi over 6 pi over beta, the saddle points are not supersymmetric, right? So I mean those contributions just go away because of the Fermi-0 mode in the partition function. Okay, so the conclusion from here is that hard derivative corrections cannot cure this problem if the geometry is smooth. Okay, so the only hope is that somehow the geometry is not smooth. Okay. So the idea is that we go back to the geometry and see if the geometry is smooth or not. So here is the point that if the geometry is not smooth, then the argument doesn't work, because there may be regions where the curvatures are large and the derivative expansion breaks down. right? So you cannot just treat this in derivative expansion. Okay. So one can ask, is the geometry smooth? Okay. And a closer inspection reveals that the metric is singular over a subspace of the horizon. Okay, it's singular, it's non-singular away from the horizon. It's also singular on most of the horizon. Okay. But there is a subspace of the horizon where the metric is singular. Okay. And in 4 dimension, this subspace is the north and south poles. But in general, it's a subspace. I'll show you what the corresponding subspace is. Okay, thank you. Okay. So the idea is that we study the solution near the subspace in the large lambda limit. Okay, and see what we get. Okay. So in the next slide, I'm going to write down the solution, okay, by focusing on the near horizon geometry and in the large lambda limit. So here is the solution. Okay, near, so the singularity in this coordinate, so this new coordinate system I have introduced. Okay, and I have also taken the large lambda limit. Okay. So in this coordinate system, okay, the singularity is essentially at r equal to 0. Okay. Now, the only part that I want you to remember from this, okay, is that most of the solution is completely universal. It has no dependence on any of the parameters of the black hole, okay, or the asymptotic model. Okay, it's a completely universal solution, okay, except for the ones that are marked in black. Okay. So this is a 4-dimensional sphere, D minus 4-dimensional sphere, and it's multiplied. This is a unit metric, the metric on the unit D minus 4 sphere, and it's multiplied by a factor of b square, where b is that extra parameter that we had. Okay. And the other place where the parameter dependence comes is in the expression for exponential of -5, the dilaton. Okay. And here also you see that there is a dependence on the asymptotic coupling, the b and the m naught parameter that the black hole had. Other than this, there is no dependence on b anywhere. And now the point is that when you try to look at what kind of corrections you will have, okay, you see that this part, because it's just a constant shift of the dilaton, okay, this doesn't enter alpha prime correction, right? It just acts as an additive term to phi, okay, whereas you know that as far as alpha prime corrections are concerned, okay, they only involve derivatives of phi. Okay, so this doesn't affect alpha prime corrections. Okay. This term, okay, looks like a decoupled D minus 4 sphere. This doesn't interact with anything else. Okay, thank you. And in the limit of large B, okay, this just becomes almost flat. Okay, this is like an almost flat space. So the alpha prime corrections to this metric are supposed to be small, right? They will be down by 1 over lambda square, which you don't care about. Okay. So here I have again written the same solution in small forms. Okay. So the way we should think about this is that these solutions provide the boundary condition at large r. At large r, the curvatures are small compared to the string scale. So these solutions should be treated as if giving the boundary condition at large r. And as you come towards r equal to 0, okay, once r becomes of order 1, the alpha prime corrections start taking over, okay, and they modify the solution. Okay. Quantum corrections are expected to be small because e to the minus phi goes as lambda for large lambda. Okay, you can do the scaling here, and this means that the string coupling at the horizon is small. Okay, so you don't have to worry about the quantum corrections. So based on this, we can argue that the net correction, okay, whatever be the form of the correction, it has the following form. Okay. First of all, CD was the overall multiplicative constant in the action, that will appear here. Okay. Then because e to the minus phi multiplies the action, it will, and e to the minus phi has this factor, it will also have a factor like this. Okay. Then it will have the volume of this d minus 4 sphere, which is thus b to the d minus 4 times the volume of the units d minus 4 sphere. And then there is a universal constant k, okay, which we don't know, that depends on the alpha, how the alpha prime correction modifies this solution. Okay. But this has no dependence on any of the parameters of the black hole, okay, because alpha prime corrections will be completely universal. So now let's collect the results. So we argued that this combination has this structure over here, okay, and now we also recall that square root of q squared, that, okay, square root of q square had this formula. Okay. Omega k is the volume of the unit k sphere, and now we have to write this formula. Okay, because you see that in one case you have omega d minus 4, in the other case you have omega d minus 2. Okay. So from this we get is this combination. Okay. I rewrite this in terms of square root of q square, okay. And we see that all the d dependence cancels, okay. And I just get k over 2 pi square root of 2 times square root of q square. Okay. And so if you compare with the microscopic formula, okay, we see that both formula are independent of d, okay, and the asymptotic values of phi and n, and they would agree if k is 8 pi square, okay, which of course we don't know how to calculate, but if we could calculate k, okay, whatever it is, it either is 8 pi square or otherwise string theory is wrong, okay, because we are now really comparing index to index, right? So there is no way that, I mean, if it fails, then there is no way out. And I should just say the same result holds, I mean, one can argue that the same result holds in any other compactification of heterotic string theory that preserves 8 or more supersymmetries. Okay. Here I have the script of the unnecessary parameters, right? And so this is what you have to solve, right? You take this universal solution. Okay. This is the compact part, it doesn't matter, compact part and this 4d minus 4 sphere, which you don't care about. Okay. Except for a circle for which, I mean, because these gauge fields come from one of the circles. Okay. So you take the geometry, which is this plus a circle, okay, and this is the solution. And the question is how to calculate take into account the higher derivative corrections, the alpha prime corrections, and compute the entropy of this solution, right? And that we want to use that to calculate this universal number k. Okay, so now just in a minute I'll just explain the relation to the work that Samit talked about in the morning. Okay. So they consider the same system in 4 dimensions, okay, and they use a very different language. They use the Lagrangian of n equal to supergravity. Okay. And what they showed is that for a special class of higher derivative terms, okay, makes the solution regular. Okay. They also made a guess for what this combination is, okay, even though it was not calculated from first principle. And based on the guess and the special class of higher derivative terms, their result reproduced the correct coefficient k, right? Which means in our language, they would have found k equal to 8 pi square. Okay. And even though they did this calculation in d equal to 4, since our result shows that k is dimension independent, okay, it shows that k has the correct value for all d under the same assumptions that were used in their paper. Finally, some open questions. Okay. So, can we justify the assumptions that they made? Okay, that's one way to try to solve this. Why other higher derivative corrections are not important, or how to calculate the explicit result for the entropy. The other approach that I have already said is to just directly construct an exact worldsheet conformal field theory that describes the universal geometry near the singularity and then compute the entropy from first principles. Okay, this is a completely well-defined problem because the boundary condition is given, right? We know how the target space should look like for large R, and now you have to basically take into account the alpha prime corrections, construct the full sigma model, and compute the entropy. Okay, thank you.
Questions? If you could calculate a worldsheet CFT, how would you calculate the entropy?
Well, presumably there is a way to calculate the action, right, from the target space. We don't know how to do this explicitly, right? But you have to somehow compute the action and then from there calculate the entropy, right? Or you can try to calculate, instead of the entropy, the derivative of the entropy with respect to charge or something, right? And then you try to extract that, yeah, some 2-point function, yeah. I mean, relate the entropy to some appropriate universal 2-point function or 3-point function, and then extract the result from there.
I had a question also about when you wrote down the equation that S BPS was equal to S world plus 2 pi ij plus corrections.
Yes.
Are you expecting a difference in the quantum corrections from the point of view of the index versus the degeneracy?
In general, yes, there could be. Right? In practice, I don't know whether it will happen or not. Right?
Okay.
But typically, I mean, the arguments based on near horizon geometry ignore the fluctuations outside the horizon, right? And they could give additional contributions which make the index and degeneracy different.
And then maybe, is there someone else with a question? Can I ask a second question? Okay. Also, the other thing I was curious about was in terms of like these quantum corrections, if it is possible for these backgrounds to compute the log A correction or not. Is that something
so maybe, did you finish your question or?
No.
Yeah. See, in principle it should be possible, but the usual approach that has been used so far in computing this log A is that the geometry that one deals with has an overall scale factor, right? And that one uses to argue that all the eigenvalues are of order 1 over that scale, and hence calculating the log of that scale is equivalent to just counting the number of eigenvalues, right? Some regulated number of eigenvalues which one uses hit kernel to calculate. For this geometry, that is not quite the case, right? Because even though the geometry scales as lambda squared, the metric scales as lambda squared, near the horizon it's string scale, right? So if some of the eigenvalues are of the order of 1 or of order 1 in string units, right, those will be counted in the hit kernel, but they don't contribute to log of area. So it is possible in principle to calculate the log of area, but you have to extract out that part, right? How much of this is log of 1 versus how much of this is the log of the area, right, from the hit kernel.
But if you're in an odd number of dimensions, I know.
Yeah, I think even if you're an odd number of dimensions, that just says that the bulk contribution to the hit kernel is 0. But that 0 may come from something that is from log A and something that is log 1, right? So you have to really know how much is the log 1.
So, I mean, you were working with the string metric here, is that correct?
All the results that I have written are in string metric.
Right. And so now if you relax this condition that beta omega is 2 pi I, and do you still get singularities at the north and south pole?
No. Once you relax that assumption, it's not the case anymore.
So it's just in that special case.
Yeah. So it's for beta omega equal to 2 pi I that you get the singularities.
Thank you.
Otherwise you get a regular horizon.
Can you go to slide 17, where you have the singular solution?
Yes.
So do you have a time angle component in the metric that is supposed to...
What component?
Time angle.
No, okay. So here, as I said, this has been written in a new coordinate system, right? And I have just diagonalized it near the horizon. So that's why the time angle component is not there. In the original metric, original coordinate system, the time angle component indeed were there.
Any further questions? Maybe I'll ask another question. So I guess the result Samir described earlier today was through the type 2A heterotic duality, and it makes a prediction about this worldsheet CFT.
Yeah. See, I wouldn't say that it's type 2A heterotic duality. They use the supergravity language, right? So you could have equally used the language purely in the heterotic description, right? You don't have to use the type 2A description for this. You could just use the heterotic description. I mean, because supergravity is the same, right? For type 2 or heterotic. Up to a duality transformation, up to the symplectic transformation on the fields. But otherwise, you could have taken their supergravity, right, just as describing the heterotic on K3 times T2.
But I thought from the type, if I understand correctly, the type 2A description, that was a one loop correction that resolved it.
Yeah, from type 2A, it's a one loop correction.
I used the 2A heterotic duality to take the shortcut to what is the paper test. In that case, it's a one loop, but it's the same paper test.
I understand that's the answer you're expecting to get, but I thought, I mean, isn't there the question here that from heterotic perspective, this worldsheet, there is no derivation of that correction from the worldsheet CFT directly?
Of that particular correction? Yeah, originally that correction was derived using type 2, one loop type 2, but once you translate it to the heterotic language, you only keep the part that is that appears at the tree level, right? Because you see that the coupling is going to 0, So you can approximate it by the part of that, because that what you calculate from the type 2A perspective involves the log of the eta functions, right? It's a complicated modular function, log of complicated modular function. But on the heterotics, this whole calculation, I think even the one that Samir described, right, takes the weak coupling limit from the heterotic side, right? So instead of getting the log of the Dedekind eta, you just take linear terms in the string in S in the dilaton field.
I think I get that. However, on the next slide, then you wrote this K that was not derived from the heterotic worldsheet description.
Yeah, it was not derived from the heterotic worldsheet description, but the coefficient of the F term will be the same, right? Whether you derive it from type 2 or heterotic, it's just low energy expansion of the theory.
I think I'm not getting something, but maybe I'll ask you after.
Yeah, and but the point is that the F terms calculated from type 2 and heterotic has to match, right? Because both are F terms, right? It doesn't matter how you calculate it.
I understand, but I'm saying that doesn't that mean that through that duality you're actually making a prediction about the worldsheet CFT, which is not solvable so far?
Yeah, probably. Yeah. Through that duality.
That's what I.
Yeah. Certainly, but it's not just through a duality. You have to make this additional assumption that the F terms are enough to calculate the. Yeah. I completely agree. Okay. Yeah. So through that duality, so their prediction for K, that calculation was done in the type 2A theory, right? The particular coefficient that was used to calculate K came from type 2A. Right. Indeed.
Thank you. Okay. If there are no further questions, we'll move to the next talk. Thank you.